Last time we began to talk about higher order linear differential equations. In particular, we're doing some preliminary theory that is talking about some of the important terminology. So let me just review real quick what we've done so far. Of course, we've made the distinction that's going to be very important throughout the entire chapter between homogeneous and non-homogeneous higher order differential equations in the case of linear, where basically that just means that the right-hand side is either 0 or not 0. In order to solve a non-homogeneous equation, we will always start by solving the associated homogeneous equation, and we'll talk later today about why that's the case. We've got a little bit started on answering the question of why that's the case when I introduced what's called the superposition principle. The superposition principle simply says that when you have a solution or two solutions or any number of solutions to the homogeneous equation, when the right-hand side is 0, then any combination of those also is a solution. Hang on just one second. Okay, so I was in the process of saying two solutions to a homogeneous equation will give you a way of writing a general solution to that homogeneous equation, meaning that a combination of those two, a C1 plus Y1 plus C2 plus Y2, gives you a general solution. Okay, now what I mean by that is that our goal eventually is going to be to find all of the possible solutions that we can. Did it not print? Okay, well, I'll get it later. Thank you for checking. Crazy morning. Sorry about that. Anyways, we're going to start with something like this. We're going to find all the possible solutions to it, and then our general answer will be a constant times the first solution plus a constant times the second solution. In this case, since it's third order, we're going to have 3 of them, and we'll talk more about that. But the main thing to remember is when I say superposition principle, I mean a linear combination of solutions to a homogeneous equation is still a solution to that homogeneous equation. It does not work for non-homogeneous, but it does work for homogeneous. Okay? All right. And we got to the point where we're talking about linearly dependent and independent functions, which we didn't talk much about in linear algebra when you guys who took it with me, when we covered dependence and independence, but we can determine whether or not a set of functions are dependent. It's the same idea that we covered. It's the same definition, in fact, for independence and dependence that we gave in linear algebra. It basically says if you take a general linear combination and set it identically equal to 0, is there a non-trivial solution to that equation? If there is, they're dependent, because that means at least one of them can be written as a combination of the rest. But if the only solution to this equation is 0, then they are independent. And that's the property we're going to want when we start talking about finding all the possible solutions to that homogeneous equation. We want all the independent solutions, not the dependent solutions. So the function lists that we get have to be independent. The way that we check whether something is independent is with this guy. Remember? Nice, good name for a mathematical operation, the Wronskian. We find the Wronskian by finding the determinant of this particular matrix. You put the functions on the first row, the first derivatives on the second row, and you keep going until you have a square one. And then this is the theorem that we use. If the Wronskian is non-zero for all values of x on a given interval, then the functions are independent on that interval. If this determinant, which is going to be a function of x whenever you actually calculate it, if that function is not 0 over some interval, then on that interval we say they are, they turn out to be independent. And so the two examples of functions that I gave you before in the solution to that differential equation earlier, y1 and y2, we proved that they are independent on an interval like this. Actually, we proved that they were independent on any interval that did not contain 0. Okay, so now let's kind of continue on and finish up talking about what kind of things we need to be looking for when we're trying to solve these differential equations. All right, so if we have a set of functions, y1 through yn, and they are linearly independent, and they are a solution to the, remember this one right here happens to be the homogeneous equation that we started with, higher order, linear, homogeneous, differential equation, then it's said to be a fundamental set of solutions. Most important thing to recognize is this number here. Okay? That corresponds to the order of the ODE. Okay? But the other very important part of this definition is this word right here. Or two words, I should say. You have n of them, where n was the order. So if it was a second order, you'd have to have 2.
You're froze. There you go.
Okay? So you have to have n of them. So if it was a second order, you will need 2. If it's a third order, you'll need 3. If it's fourth order, you need 4. You need that many to have a fundamental set. And they also all have to be linearly independent. Okay. The theorem here simply says that there is such a fundamental set, that it always exists, that you can find that many linearly independent solutions to that differential equation. Okay. And that blank should be such that what? What do I mean to say there? I'm going to call them y sub I of x is an element of C0 over some interval I. That's there's a fundamental set over an interval I where those solutions are C0. Do you remember what C0 means? You've seen it before. It's a very important word when you talk about functions. We like these kinds of functions above all else. Starts with the word C, or letter C.
Continuous.
Continuous. They are continuous functions. By the way, C0 would mean that just the function itself is continuous. If I say C1, I mean continuously differentiable, which means the function's continuous, it's got a derivative, and its derivative is continuous. C2 is the function is continuous, its first derivative is continuous, its second derivative exists and is continuous. And so on. Okay. All I'm saying is that we've got a fundamental set so that all those functions are continuous on the interval for every I from 1 up to n. That's a powerful theorem. I mean, the fact that I'm omitting the proof is kind of negligent on my part, but I'm going to go ahead for the sake of time and not prove that. But the idea being that we know we can always find a fundamental set for all versions of equation 2. And just, I haven't looked at it in a while. I'm going to scroll fast up. There's equation 2 right here. Right? It's the linear form of a homogeneous nth order differential equation. Okay. So, we know it exists. We're going to spend the rest of the chapter finding it. Okay, now, if that fundamental set is given by y1 through yn, then the general form of the solution is to put these constants in front here. That is, take a linear combination of your fundamental set. Okay, well, the easy proof of this is to make use of it's the main reason I included that whole section where we talked about linear differential operators. Remember that I can rewrite equation 2 is the same thing as Ly equals 0. Remember I introduced that L notation to represent the differential operator that was on the left-hand side of that equation. Okay, so what we would want to show is that L of C1y1 plus C2y2 plus dot 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 CNYN is 0. But that's easy to show because that right there is equal to C1 L1, no, Ly1 plus C2 Ly2 plus dot 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 plus Cn Lyn. Because we talked about this, that's what it means for L to be linear, is that you can split it up across sums and you can pull all the constants out. But then all of these are 0 because y1 through yn are all solutions of equation 2 by themselves. Right? Since yi is also a solution to 2. So that's equal to 0, which is the proof. That's why it's so short. And again, what I'm doing, I'm taking advantage of the fact that we have this whole section in these notes where we were able to rewrite equation 2 as Ly equals 0, as a linear operator applied to y. Done. Okay, so if I said we have 3 equations, y1, y2, y3, are all solutions to this differential equation right there. I'm actually giving you that. I'm not asking you to show that. What I do want you to do is show me that they form a fundamental set of solutions. Okay? So we're going to assume they are solutions, which you know how to check. We did that as far back as chapter 1, right? Take the first, second, third derivatives, plug them all each into here. You'll see they work. So the question is, how do we prove by definition that these are a fundamental set? What does it require for it to be a fundamental set? Here's the definition right here. First of all, there needs to be n of them. What is n? Order. So what's the order of this differential equation? 3. How many solutions did I give you? 3. Check. Done. Okay, what else has to be true for it to be a fundamental set? How do we check that?
Check if there's a, make sure that the, whatchamacallit solution is the only solution? Trivial solution?
Right, so we could do it by the definition. The only one that we did by definition was the that sine squared and the cosine squared and the secant squared and tangent squared example. That's the hard way, and rarely will it work. I mean, rarely will you be able to find if there's a trivial or non-trivial solution. We know the trivial solution always works, but finding a non-trivial. So, what's the easier way?
Wronskian.
Yeah, so we're going to use the Wronskian. Okay. Which to show linearly independent. Okay. So the Wronskian of e to the x, e to the 2x, and e to the 3x is a determinant goes on the first row.
E to the x, e to the 2,
Okay. Next row.
e to the x, 2 e to the 2x.
What am I doing?
Derivatives.
Second row is the first derivative. Third row is the next one. So e to the x, 4e to the 2x, 9e to the 3x. And here's where you got to remember how to take a 3 by 3 determinant. Forward diagonal plus forward diagonal plus the forward diagonal. You multiply along those diagonals. So you get 18 e to the 6x, right? E to the x times 2e to the 2x times 9e to the 3x. 1 times 2 times 9 is 18. E to the x times e to the 2x times e to the 3x. You add the exponents, you get e to the 6x. Plus 12 e to the 6x, right? 1 times 3, nope, times 1 is 3, sorry. Jumped in. It's following this one here. And then e to the 3x times 4, e to the 2x times e to the x gives me a plus 4 e to the 6x. And then you do the back diagonal. And you subtract them. So minus 1 times 2 times 1 is minus 2e to the 3x plus 2x plus x, again is 6x. Minus 1 times 1 times 9 e to the 6x. And 1 times 4 times 3 is minus 12 e to the 6x. $18 plus 3 plus 4, 25. 25 minus 2 is 23. 23 minus 9 is 14. 14 minus 12 is 2. Does that make sense? Now, that's the Wronskian. So the output of the Wronskian was this function. How do we use that to answer the question, are they independent or not? Go back to the theorem if you need to. There's a theorem right after the Wronskian.
If it's not equal to 0.
Okay, so 2e to the 6x. We need to check where that's 0. Anywhere it's 0, any interval containing that point, they're dependent. What about 2e to the 6x? Is that 0? Where is that 0?
Nowhere.
Nowhere. That's never 0, right? E to a power, whether positive or negative, is always positive. Not 0 for all x, which means they are linearly independent on the entire real line. So that's how we verify that that's a fundamental set of solutions. Which means fundamental set. The next question is then what is the general solution? If we know this, this, and this form a fundamental set, then the general solution, you just write it down immediately. It's going to be C1 times the first function plus C2 times the second function plus C3 times the third function. That's your general solution to the homogeneous differential equation we were given. Okay. Notice how this kind of jives with what we've been doing before, where when we had a first order equation, we had one C unknown in it, right? If we have a second order differential equation, we have two C's. That will match. That's where our C's come into play. And then if we were given an initial value problem, that's when we plug in initial conditions to find what those C's would be. But now what we've got is we know where the C's come up in this problem. The hard part's going to be, can we find the E's that go to this? Actually, that's not the hard part. That's the easy part. But even easier is the part where you just write down the solution when you're done. Okay, but that's all to do with equation 2, which was the homogeneous case. What about the non-homogeneous case? What happens when the right-hand side here is not 0? Sounds actually pretty easy. Look at what this theorem says. Let YP be any particular solution to equation 4, the one I just have right there above this on the screen. Y1, Y2 through Yn are solutions to the associated homogeneous equation. So change the right-hand side to 0, find all of your N solutions to that problem. Then to write your general solution to the non-homogeneous is simply the solution Y sub H, I would call that, which is the solution or the general solution to the homogeneous version. And then plus just any one particular solution you can find. Find one single particular solution to the non-homogeneous equation. Then your general solution is the solution to the homogeneous version of that equation, plus that one tiny little particular solution on the right-hand side. If you can do that, you have found a general solution. Now, how do you know that's a general solution? How do you know that works? Well, I'm going to do it by checking Ly. And since I want it to solve equation 4 up here, I need Ly to equal g of x. That is where this is the y I'm plugging in right here. If I show that, then I will have shown that y is a solution to 4, and because it has c parameters in it, it has all these parameters, there's n of those c's. Since those are an n parameter family of solutions, then that will form the general solution to equation 4. That's essentially what I'm going to prove. Okay? Now we know we're going to let y1, y2, all the way up to yn be a fundamental set which I know exists because it's given. I'm going to let that be the solution to the homogeneous equation for the equation Ly equals 0. Again, right-hand side, 0. When I write Ly, this right here means Ly. Okay, so those are solutions to this, which means, by the way, what's true for every single one of those? What's L of any one of those y's? 0. Okay. So now consider L of C1Y1. Oh, by the way, before I write that, hold on. We also know that L of Y sub P is equal to what? Well, I said let YP be a solution to equation 4. So what does L of YP then equal?
Not zero?
It's not 0. In particular, it's a solution to this. So if I plug in a YP, I'm saying I plug in YP on the left-hand side, work it all out, what am I going to get?
G of X.
G of X. So this is G of X. That's what it means for YP to solve 4, whereas all the YI's, 1 through N, they solve Ly equals 0, which is what we called equation 2 earlier. But now what we want to check is Ly for this particular Y equal to G. So L of C1 Y1 plus C2 Y2 plus all the way out to Cn Yn plus Yp. Question is, what does that equal to? When we use what we've already stated to prove that. So what can we say this is equal to? We don't know that yet. But what can I do to it? I mean, that's what we want to get to, Matt. We want to show it's g of x, but we got to be able to explain why. So what can you do with a linear operator like this? We can split it up, right? Split sums, pull all the constants out. So this becomes C1L of Y1 plus C2L of Y2 plus all the way out to CNL of Yn. I'm basically distributing this function. I can distribute linear functions. Those are the types of functions I can distribute. And I can also pull constants out, because that's what it means to be linear, plus a L of Yp. And what's L of Y1? Zero. L of Y2? L of Yn? 0. And L of Yp?
G of X.
This whole thing equals G of X. Okay, so what this theory tells us we can do is, in order to solve a non-homogeneous equation that looks like that, we've got to find the homogeneous solution in general, and then we've got to find one particular solution. Okay? So to solve a non-homogeneous ODE, top of page 7, are the steps. Solve the associated homogeneous, then find one particular solution, and then the final solution is the sum of those two. That is the general solution plus that one particular solution. Okay? Just, by the way, I'm going to jump ahead. The blanks at the bottom of page 7. How do we find the homogeneous solution? That's going to be what we cover in the next section, 4.3. And then how do we find the YPs? Well, you can probably guess by the number of sections this involves that that's the harder question. Section 4.4 through 4.6. Actually, the truth is, I didn't tell you you were doing this, but you've already solved homogeneous equations before in on the test you took for me for the first test. We did a problem like that. You'll see that in just a minute when we get to 4.3. You've already done it. Okay, so let's just to kind of reinforce this, let's come back to this guy, which you'll recognize the equation on the left-hand side matches that problem on page 5, or was it page, Where was it? Oh, yeah, at the bottom of page 5. Y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. Okay, previous example was the homogeneous version. That's just so that you recognize that. Okay, YP. Show that this particular function is a particular solution to this differential equation right here. All I'm saying is verify that it's a solution, in the sense that this doesn't have any parameters in it, so it's a single, one and only one solution, so that's why I call it particular, but I just want to verify that it's a solution. So I need to do yp prime, yp double prime, and yp triple prime, and plug all those into this, and see if the left-hand side equals the right-hand side. So first derivative is just negative 1/2, right? And then these are 0 and 0. So plug in, and I get 0 minus 6 times 0 plus 11 times negative 1/2 minus 6 times negative 11 halves minus 1/2 x. That's right. Y, third derivative is 0 minus 6 times the second derivative, which was also 0, plus 11 times the first derivative, which was a negative 1/2, minus 6 times the original function, which was minus 11 halves minus 1/2 x.
Is that 11 halves or 11 twelfths?
Here's 12ths. Yep, that was just me not writing that. So 0, 0, I get a negative 11 halves. Distribute this. Negative 6 times negative 11 twelfths is now plus 11 halves. Plus what? Negative 6 times a minus 1/2 is plus 3x. Okay? Verified. It is, in fact, a particular solution because when I plug that yp in, I do get 3x. Again, finding this y sub p is the purpose of several sections in this chapter. Finding the y sub h is all of 4.3. Okay? What's the general solution? To this differential equation now. If I asked for the general solution, you have to combine what work we did in the previous example with this one, because the general solution is the solution to the homogeneous version plus the particular solution. So what was the general solution? What was the solution to the homogeneous version? What was the y1 in the last one? E to the x plus c2 e to the what? 2x plus c3 e to the 3x, and then
Plus px.
nope.
You see, I didn't do that. Oh, 1 of p.
What's y3?
Which in our case would be minus 11 twelfths minus 1/2 x. Okay. So that's your preliminary theory. Again, all this is to say that the way that we find the solution is to find the fundamental set of the homogeneous plus find one particular solution. You take the linear combination of your fundamental set plus your particular solution, and there's what your general solution looks like. And so there's some theory in here about why that works, several proofs that prove that the fundamental set, well, we didn't prove that the fundamental set exists, but it does prove that the fundamental set, we did prove that the fundamental set actually is a solution, and we take its linear combination. I'm going to skip over 4.2 just for the sake of time, and I don't see it as really all that valuable to what we need to accomplish or any of the types of projects we're going to be doing in here when we get to that. So I'm going to stop the recording for this.